when W is a subspace of finite dimensional vector space, then dimension of V by W equal to dimension of V minus dimension of, means that quotient space generated by W has dimension equal to dimension of V, means dimension of vector space minus dimension of W. Okay, so we will prove this theorem. So since W is a subspace of vector space V and V is finite dimensional vector space, so W will also be finite dimensional vector space. So W will also be finite dimensional vector space because W is a subspace and V is finite dimensional, so W will be finite dimensional. Now, what does mean by finite dimensional vector space? Finite dimensional vector space mean by we have a basis of W which cardinality is finite. Okay, so we have a basis to assume W1 dot to Wn be a basis for W. Since it is finite dimensional, we have finite number of element in the basis. So we assumed W1 W2 dot Wn be a basis for W. Now this is basis, so it will be linearly independent in W and it will span W. Both condition will hold. So W1, W2 dot Wn are member from V. Now it is member of W and W is contained in V. So W1, W2 dot Wn are member of V and it is Li. Okay, it is Li. So these all member are Li set of V. Okay. Now by extension theorem, any linearly independent set can be extended to form a basis of V. So if V is vector space and if we take any linearly independent set, okay, V1 to Vk, so it can be extended, means we will add some more vector to this set to form a basis of V. Okay, so assume W1 to Wn and we have added some more vectors V1 dot to Vk be basis for V. Now we have extended W1 to Wn to form a basis of V by adding some vectors V1 to Vk. So this is a basis of V. Okay, and W1 to Wn is a basis of W. Okay, we can see here W1 to Wn is a basis for W. We will use this fact. Okay, now we claim that V1 plus W, this vector plus W, V2 plus W dot Vk plus W be a basis for V by W, means that these vectors will form basis of V by W. Okay, if these vectors form a basis, then how many vectors we have here? V1 to Vk. So we have k vectors. And now we know that k can be written as n plus k minus n because this will be cancelled out. This will be cancelled out. Remaining will be k only. And we know that n plus k be the basis for V, means dimension of V is n plus k. From here we can tell. So it will be n plus k is the dimension of V and n is the dimension of W. Okay, we can see here because W1 to Wn be a basis. Okay, W1 to Wn is a basis. So this will imply dimension of W equal to n. Okay, so we have dimension W equal to n. So it will be dimension of V by W equal to dimension of V minus dimension W. And that is what we have to prove. So if we were able to prove dimension of V by W equal to K, we are done. Okay, so now we are trying to show V1 plus W dot Vk plus W is a basis for V by W. In the proving basis for V by W, what we will prove? We will prove that it is Li. These elements are linearly independent and it will span any element of V by W. Okay, so first we will prove that this is Li. So take any arbitrary element. Okay, let A1 dot to A K are from field such that we have taken some arbitrary element from the field such that A1 dot, here the operation is dot. Okay, A1 dot V1 plus W dot plus dot AK dot VK plus W equal to 0. Or we know that the zero vector of V by W is itself W. That's why we have taken here W. Okay, we can write here 0 vector of V by W. Okay, because we are working in the vector space of V by W. Okay, that's why we have taken the element of V by W and their linear combination should be equal to 0 vector. And 0 vector from what? 0 vector from vector space V by W. Okay, so using definition of dot operation. Okay, so what is the definition of dot operation in V by W? So A dot V plus W is equal to AB plus W. Okay, we have seen in previous lecture that, so it will be A1 V1. If you multiply A1 to V1 plus W, A1 V1 plus W. Similarly, it will be AK VK plus W, and this is W. Okay, now using definition of plus operation, we have two operation on any vector space. We have two operation, one is dot, one is plus. So plus operation, how it is defined in V by W. So take one element V1 plus W, take another element V2 plus W, and if we add this, it will be equal to V1 plus V2 plus W. Okay, this is the definition in V by W vector space we have used. Okay, so now if we add these vectors, what will be LHS? So if we add A1 V1 plus W plus A2 V2 plus W, what it will be? It will be A1 V1 plus A2 V2 plus W by definition. So if we add two vectors, we got this vector. So if we add k vectors, so if we will get A1 V1 plus dot dot AK VK plus W equal to W. Now what we know that if V plus W equal to W, it will imply that it is both part. Okay, if and only if condition, V should be in W. So we will use this fact that A1 B1 plus dot dot AK BK. This is nothing but a vector. Linear combination of vector is again a vector. So it will be in W. Because it will be in W, so A1 B1 plus dot dot AK VK equal to W for some W belongs to W. Okay, now we have, since this is element of W, so this can be written as V1 W1 plus dot dot V and Wn for some scalars B1 dot dot Bn from field, because we have assumed that W1 W2 dot dot Wn is a basis for W. So any vector can be written as a linear combination of basis element. So this W can be written as B1 W1 plus dot dot Bn Wn. Now if we take these vectors, this vector in LHS, what we get, we will get a1 b1 plus dot ak bk minus, because LHS was in plus, so it will be minus b1 w1 b2 w2 minus dot minus bn wn equal to 0. Now what we know that w1 w2 sorry wn v1 dot vk is a basis for v. We have extended w1 to wn to v1 to vk basis for v. Since this is a basis and it equal to 0 vector, so their coefficient, all the coefficient will be 0, because basis are the Li vectors. Okay, so ai is equal to 0 for all I vary from 1 to k, and bj equal to 0 for all j vary from 1 to n. Okay, so our aim was to show ai is equal to 0, because we are going to prove v1w plus dot vkw is Li vectors. So our aim was to show ai is equal to 0, and we are done here. Okay, so ai is equal to 0 for all I vary from 1 to k. It means that v1 plus w dot vk plus w, these vectors are Li vectors. Okay, now to show v1 plus w dot vk plus w spans v by w, we have proved that these vectors are Li. Now we will prove that these vector can span every element of v by w. Okay, so let's assume any arbitrary vector from v by w. So any element of v by w will be form of this v plus w. So now for some constants a1 to ak and b1 to bn from field, this v vector is from capital V vector space, and what we know that v1 to vk, w1 to wn is a basis. So basis of vector space capital V. So we can write this vector, the linear combination of all these vectors. Okay, so that's what we have written here, a1 b1 plus dot ak vk plus b1 w1 plus dot bn wn plus w. But what we know that b1 w1 plus dot bn wn belongs to w, because w1 to wn was a basis for w subspace, so it is in capital W, or this is capital W, so v plus w, what will be equal to v plus w, because this member is in W, so it will contain in W. Okay, now we have left here a1 v1 plus dot ak vk plus w. Now we can use the definition of plus and dot here. So what we get, a1 v1 plus w plus dot ak vk plus w, using the definition of plus operation, and here we will use the definition of dot operation to get a1 dot v1 plus w plus dot ak dot vk plus w. So for any element v plus w, we can write this element as a linear combination of v1 plus w vk dot vk plus w, and say these elements can span a whole vector space v by w, and this was Li, it means it is a basis, and our aim was to show that this is a basis. Okay, so we have proved here. So if you like this video, please subscribe my channel for more videos. Okay, thank you.